Welcome to the 8th and final lecture of our 9th unit, Momentum and Impulse. This is going to look at the center of mass of a system of particles. So it wouldn't hurt to review what center of mass is. Your textbook gives a good definition, I think. The center of mass is the special point within an extended body that moves as if all of the mass of the system were concentrated at that point. So this is sort of like when we did analyses with extended bodies and we had to figure out the gravitational force, and we would always just draw the gravitational force vector originating at the center of mass. Even though gravity really acts on all the particles, it's valid to sort of pretend all of the mass is located at the center. We do need to calculate center of mass separately in each dimension, and then you can add them to find the total three-dimensional location of the center of mass. And we used this formula in each dimension to find center of mass. It's a little bit complicated looking, so I tried to simplify it in the next bullet. But first, let's look at this symbol here. So this is the sum out to particle I, which is the last particle in the system, however many particles there are, of x, which is the distance from some reference point, times the mass of each particle. And then you divide by capital M, which means the combined mass of all of the particles in this system. So what this is really doing is just taking a weighted average, right? We're going to multiply the mass of each individual particle times how far away that particle is from the reference, and then divide it by the sum of all of the masses. Another way of expressing the same thing is if for any number of particles, I particles, you could take m1 x1, so the mass of particle 1 times its distance from your reference point, plus m2 x2 dot dot dot, so out to however many particles there are, the ith particle, and then divide that by the sum of all of the particles in the system, and that'll give you how far from your reference point the center of mass is located along a single axis. They come together, and their joint center of mass is located roughly here. Again, that's 0.33 meters or 33 centimeters to the right of the spot I marked 0. But I wanted to prove to you that if you had started from a reference point located at the center of mass of the left skater, you get the same point in space. So your answer would have come out as 1.33 meters, but that would be 1.33 meters from her, which is exactly in the same spot, or 0.33 meters from the 0 spot, since she started 1 meter to the left of that. The total linear momentum of a system is equal to the total mass of the system times the velocity of the center of mass. So let's think about the skaters again. Before they began moving, their total momentum was 0. After they both began moving in different directions, their center of mass stayed in the same spot. Therefore, the center of mass had 0 velocity even after the push. That is a proof that momentum was conserved. The total momentum of the system was constantly at 0. We could also say the center of mass of an isolated system does not move. And remember, isolated system just means that momentum is conserved because there are no external net forces. And I like this from the book. I took this from page 274. If the system is not isolated, then the center of mass moves like it were a particle of mass big M, which would be the sum of each particle's mass, under the influence of the resultant external force on the system. In other words, it's valid to pretend like these two skaters are a single object of mass 150 kilograms located at the position 0.33 meters and don't move. Even though each individual skater moves, their center of mass doesn't because momentum is conserved. If we see a problem where momentum is not conserved, a system is not isolated, we can just use Newton's second law and apply it to a system of particles. So sum of forces external to the system is equal to big M again, meaning the mass of all the particles in the system, times A sub cm, meaning the center of mass acceleration. And because we proved this in the third lecture, I brought it back here, that would also equal the rate at which the system's momentum changes, or dp total. P total for the skaters was always at 0. Therefore, there was 0 change and 0 rate of change in the system's momentum. Therefore, there was 0 acceleration of the system's center of mass, which is a proof that there is no net force acting external to the two-skater system.